this. Okay. A little bit of, oh, there's a camera on. You don't have to have your camera on. Because I can't see you anyways. Let's see here. Kind of threw me off. All right, we are recording. So I forgot to post the tables. So the Z table, and then we will have a T table as well, but it'll be a while. So under course material now, there's this tables document in case you want just a PDF of the Z table, negative side, positive side, and then don't be thrown off by the T table. It looks very similar, and it is, but we're not going to use it until chapter 5 briefly, and then majorly in chapter 7. Okay, so it'll be a while, but they're all in there. It's another thing I wanted to remember last week, Tuesday off, wasn't that so nice? And then we started section 4.1, which was on the normal distribution. And then I made a mistake, and I forgot to warn you that you probably won't be able to do most of these assignments yet. Okay, we're gonna finish it today, don't worry. So I had a couple of, I don't know how to do this. This is not what we did in class. We were building up to it. We're building up to it. So the normal distribution, as well as the binomial, which we'll cover this week, is on test 1. Okay, and so that's why I made the due date for assignment 6 is on Monday before the test. Kind of force you to do it before. Okay, I won't do that for the binomial, but it is on the test, so it's worth doing it beforehand. Check it off your, cross it off your list. Okay, and so any questions about those assignments now that I've said we're going to keep covering it? So after today, you'll be able to do it. How about that? If you tried it, good for you, that's great. But we'll keep working through section 4.1 today. And I did post practice for test 1. I'm being lazy. I know, bad. And so for the practice for test 1, what I do is I give an approximate breakdown of the grades. Now this is an old breakdown, which includes the random variables, which I will not test you on. Okay? And so I just want to highlight, right? And I'm gonna screenshot this and bring it in. Whoa, sorry. Should warn you before I take a screenshot, I guess. Notice that I call it practice for the test, not practice test. It's way longer than I expect you to do on a test, right? And so the breakdown gives you an idea of what to expect, okay? But I also want you to see lots of different types of questions, right? And so it's practice, and I'll highlight for test 1. So rough grade distributions. Okay. Question 1 is kind of what type of study is this? What type of variable is this? Looking at some visualizations. What are some appropriate visualizations depending on the variable that you have, right? Chapter 1 stuff. Now this is going to be multiple choice. Okay. Are there, is that from the speakers? Or is it me? I'm going to go in and just mute everyone up. I don't think that's how you say it. Mute everyone up. Mute all. Yes. Kind of like a rude way of saying it, I guess. Sorry about that. Okay. Question 2. I like to break it up. We move into the 5 number summaries, the outliers, right? How do you determine if you have any outliers? the shape, center, and spread, right? Which is from chapter 2, which will also be multiple choice. Okay? And so far we've got 10 marks multiple choice, right? Which usually they tend to be hard, right? Multiple choice is hard, right? So you need to know what the answer is and then pick the right one. Question 3 and 4, contingency tables. And I think these are questions, am I referring to, oh, with reference to questions in this practice test. So in the practice test, both question 3 and 4 prepare you for 5 marks is how you would read it. Things like contingency tables, probabilities, just properties of probabilities, and probability distributions, right? For 5 marks. For 4 marks, roughly, conditional probabilities using a tree diagram, everyone's favorite thing, right? And so that's from chapter 3. And then this is the one, this is from random variables. But because I only gave it to you as a bonus, right? If you wanted to, it's not on the test, don't worry. Sometimes I test it, sometimes I don't, depends on how much time we have. Okay. And so question 6, what this means is you can skip question 6 in the practice test. You can do it if you want, but I won't test you on it. That's not a trick. I will not test you on it. Okay? Not out to get you in any way. There is always a bonus question, but it's a bonus. So, and it won't be the random variable. Again, not out to get you. It'll be something that we talked about in class, something that you know. Then another 5 marks, normal distribution question, where you either have to find the probabilities or find the cutoff values. Now that's something that we're doing today, right? And so we're kind of cutting it close here. I think you got it. And then depending on how far we get into the binomial distribution, I tend to adjust this. So I hold off on printing the tests until I know where we're at. And so again, I'm kind of trying to stay flexy here, but roughly 4 marks for the binomial distribution to find probabilities, which is on Thursday. Yeah.
Is the test approximately 7 to 8 questions?
No, it'll be roughly like this. Roughly. Can't remember. Sometimes I split, let me think. No, roughly 7 or 8 questions. Depends on how you count your multiple choice. That'd be 10, but I make them parts, so. Is that again? Keep having to mute everyone. This is on Thursday. All right. Hopefully we'll get there today, just to introduce it. But I don't have a good feeling. Test number 1 is on Tuesday. I know we're heading into a long weekend. So it's right after the long weekend. So I know. Tuesday, October 14th. But just how the cookie crumbles. And I apologize. Okay. In terms of review, just do some quick review, right? What are some normal distribution facts? All right, we talked about the normal distribution. Now the normal distribution is going to be a really big player for us for the rest of the term. And so even if it feels kind of, I don't know what to do here, right? We're gonna work with it, get to know it better and better, and it will feel better as we go. Just got to give it time. Now the normal distribution looks like this with a center at the mean. right? And usually we are given some standard deviation, right? In fact, for all these questions, I'll say blah, blah, blah follows a normal distribution or an approximately normal distribution with a mean of this and a standard deviation of this, right? As soon as you see something like that, your brain's gonna go, oh, I think I have to make this something that looks like this, right? You don't have to, but it really helps to visualize the problem. Right? And we can do things like if I have some value x here, right? I can find probabilities associated with this value of x, right? And so what does that hinge on? Well, it relies on the area or the probability is the area under the curve. So if I want to find the probability of being less than x, right? Really what I'm asking you to find is this area, right? How do we do that? Well, I like to think of it as kind of a two-step process, right? Or two phases, right? So I have some x, some observation that I'm interested in. I have to morph it into a z, right? How do I do that? I use the formula that we have, that we developed last day, right? Z is x minus mu over sigma. Right? So that's how I take an x. You'll always have mu and sigma, right? And so I'll give them to you. Okay? And from the question, you'll know what x is. So then you can solve for z, right? That's going to be a standardized value, with a mean of 0. Do you remember z follows a normal distribution, shorthand, with a mean of 0 and a standard deviation of 1, right? That's that shorthand that we introduced last week. So now Z is on kind of this, I imagine it being a miniature scale, right? We kind of shrink it down. It's just a mini version of the original. And from Z, the reason we needed that Z is because our ultimate goal is to find the probability. Right? In this case, maybe we want to find the probability of being less than x. So now, once you have your z, that's when we do it old school, on the test at least, right? You'll just have the table, right? Or if you can figure out your calculator, a lot of calculators calculate the probabilities for z as well. But that's not something that I'm expecting you to do, but you're welcome to use it if you know how. We use the Z table. Use the Z table to find the probability. Right? The probability, right, in the Z table, it gives you the area to the left of some Z score, right? And we'll practice reading the Z table again today. But the Z table only gives you the area to the left, which happens to be the area you want in this quick example here. Right? But sometimes you want the area to the right, which means you have to leverage the fact that the total area is 1. Right? Whoo! Well, I alluded to it, but today we'll see it. But we can also work, if I give you a probability, right, you can work backwards. I call it working backwards, or finding the cutoff point, right? Finding your x that makes some probability happen, right? What's the lowest 10%, the highest 15%, right? That kind of thing. And so then you have some probability. You still use the Z table, but you have to use it backwards, right? That's why I call it working backwards. Right? And so then once you have your Z, you map back to your Z, then you can solve for X. Right now you'll have your Z and you can rearrange and solve for X, right? And so then you get X is, and I'll match the order, mu plus Z sigma, right? Multiplied by sigma and then add mu, and then the order is different for some reason, but that's okay, on your formula sheet. Right? All you really need is this bottom formula. Okay. Any questions before we pick up? There was an example that I left you with. Call this the end of the review. So this slide is from last week. Here it is again. I think it's nice to have a visual of kind of the procedure, right? Because there are 2 steps to it, right? In either direction. I had to keep this slide though, because it has all the information that we need and it's been a week. So, or not quite a week, I guess, since we saw it, but we've got the catch-up factory and the amounts are approximately normally distributed with a mean of 36 and a standard deviation of 0.11. We're also told that if the amount of ketchup in the bottle is below 35.8 ounces or above 36.2 ounces, then the bottle fails quality control inspection. And we figured out what percent of bottles have less than 35.8 ounces of ketchup. All right. And so what did we do? We said, okay, well, 35.8, that's my observation that I'm interested in finding a percentage with. Percentage is a probability, is an area under the curve, right? So from this 35.8, it's centered on 36, and we're told the standard deviation is 0.11. We were off to the races. First thing we did was we converted this 35.8 to a Z-score, right? So we start over here and we solve for Z. Now, because we're using the Z table, we have to round properly to 2 decimal places, which you don't have to memorize that. You would get to your table and say, oh, I only get 2 decimal places, so I need it to match, right? So rounding properly, you get negative 1.82. A Z of negative 1.82, which means what? Means that 35.8 ounces is 1.82 standard deviations below the mean of 36. Right, that's what that negative means, it's below. Then I introduced 2 options. You can write out exactly what you're finding, right? Using the Z table, we find the area to the left of Z equal to negative 1.82 is 0.0344. Therefore, 3.44% of bottles are, this should say underfilled. Underfilled? Just said Durfilled. I wonder where it went. That's wordy, but it's not hard, right? It's just tedious to write it out. But to do it properly, you should write it out. Or if you feel comfortable, you're allowed to use probability notation, but I expect it to be correct, obviously. So that feels risky, right? Unless you're very comfortable writing probability notation. So as I mentioned, I will show you both, right? Just to see if you're getting there, right? But the shorthand of this entire sentence would look like this. The probability that Z is less than or equal to negative 1.82 is 0.0344. Huh? That's some pretty good shorthand, I think. Right, saves you a lot of writing, but it's not very easy. So your choice, those are your only two options. Right? Write it out in words, right? What you did, blah, 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 or with the shorthand. Okay. Then I said, try this for Tuesday, probably desperately. I can't quite remember. Try this for Tuesday as you're all packing up. Try it on your own. What percent of bottles pass the quality control inspection? So, what does that mean? We want to find a percentage, okay, which means I want to find an area under the curve. Okay? I like to ignore all the multiple choice options until I have an answer, obviously. First thing we're going to do, it went away, is draw our normal distribution. Okay? So this is referring to the same information as before, where mean is 36, so mu is 36, and the standard deviation is 0.11. And we were also told 35.8. I already kind of jumped to it earlier, I guess, but 35.8 ounces, anything less than that is considered underfilled. And similarly, 36.2 ounces, anything over that is considered overfilled. Which means, I'll shade it just this once. This area is going to be the probability of passing the quality control inspection, which is the same as the percentage, right? All those P's mean the same thing, right? So we want to find this area between these two values. We have to get a little bit creative, and there's lots of ways that you can do it, right? Remembering that the total area is 1. My go-to move is to recognize that the total area here is 1. We already found that this area is 0.0344 from earlier, all right? Which is why we had to talk about that, all right? I can remove that from the total area of 1, right? And what if I do the same thing on this side? I just find this area that I want to remove and I subtract it from 1, right? So you can just subtract the areas you don't want, yeah? And that'll get you the area that you do want. So they do just add up to puzzle pieces that have to add to 1. Right? What's another way you could solve it? Like I said, kind of confusingly, there's lots of ways that you can solve it. What if you found this area, right? The area to the left of 36.2, right? And then chop off the area to the left of 35.8. That would get me the area I want, right? So it doesn't matter how you solve these, right? There's some really crazy ways that you could do it. What could you do? You could say, oh, I know what this area is, and I know what this area is, and add them up, but that's gonna be way more work. Could do that though. Huh? So what I want you to think about is just what makes the most sense to your brain, right? And then just do that. Huh? Because there's no sense in memorizing my way if you just intuitively said, oh, obviously, total area is 1, lob off those ones I don't want. That seems nice, right? Or with practice, right, you might gravitate towards this method where you find the area to the left of 36.2 and then chop off the area you don't want from that. Right? I'll use that method, but you'll see they work out to be the same, of course. Why do I like this method? Because the table only gives me the areas to the left, right? So if I wanted the area to the right, it's not a big deal, right? But it's an extra step that you don't actually need to do. Right? So as long as you are okay thinking about them as little puzzle pieces, you can take away and you can add them up, and as long as they add to 1, you're good, then you'll be able to solve these problems. Okay. So we already found this area. If we hadn't, we would have to do that, but to save us a little bit of time, we're just going to jump in from here. So now I have to standardize the 36.2. Right? So Z of 36.2. So sometimes if we have multiple Zs that we're working with, this is a 36. I put a little subscript on there, right? Z, upper, lower, that kind of thing. You can, it's really just for you to remember. It doesn't do anything. Yeah. And so this is the Z for 36.2, which is going to be X minus mu over sigma. It's on your formula sheet, of course. Z is 36.2 minus 36 divided by 0.11. Can take a wild guess. I think I already complained about it last day, that it was a boring cutoff, and this is why. It's the same Z, it's just positive. We expected that though, right? Because 35.8 is 0.2 below the mean and 36.2 is 0.2 above the mean. So of course they should have the same value for Z. But we can still move ahead. That's all right, even though it's a boring value. We still need 2 decimal places rounded properly, right? And so now, using the Z table, we find collectively the area to the left of Z equal to 1.82, right? Notice that I always do the area to the left because that's what the Z table gives us. If I need the area to the right, I would have to add on to my sentence afterwards. So on your table, and again, if you don't have one, I brought some spares so you can practice. Now this is a positive Z, so you want to make sure you're on the positive side. All right, what's a nice check-in point? Once you pass the mean, you know the area or the probability has to be more than 0.5, right? And so that can be kind of a way to check it. 1.82. I find that the area to the left of the Z of 1.82 is 0.9656. Oh. So then, using the Z table, we find the area to the left of Z equal to 1.82 is 0.9. Uh-oh, I lost it. Better go back. 9656. Blab too much. So if you wanted to, right, we could write 0.9656 up here. Instead of sometimes I find the shading helpful. Most of the time I find just the arrows a little bit cleaner, right? But they're both talking about the areas. If you wanted to find the area to the right, you know how to do that, right? If you wanted to, in this case, we don't really, but we can. 1 minus 0.9656. I don't even need a calculator. And that's not to brag, because I would. But why don't I need it? By symmetry, it has to be the same as on the lower end because I moved the same distance, right? And it's symmetric. So just knowing that they're the same distance from the mean, right? If I know the one area, then I also know the upper area. Again, that takes practice and time, right? To start to figure out all those clues, but really hope it's true. 1 minus 0.9656. Don't worry, I feel really good about it. Is 0.0344. So it'll be the same as on the lower end because I moved the exact same distance, right, from the mean. Okay. Same as underfilled by symmetry. That's not always going to be the case, right? But in this case, if you get the same Z, it will be the same. Yeah.
I thought you said all those numbers have to add up to 1.
Mm-hmm. So if you do, but we're double counting this 0.0344, right? And so this 0.9656 keeps going to negative infinity. And same with this 0.0344. So all the areas, if they're distinct from each other, have to add to 1. But yeah, there's some overlap there. And that would do it. So as you get more comfortable with how this distribution behaves, right, you're allowed to take little shortcuts. You could say, oh, well, I know this is 0.0344 just by symmetry. Right? That tells me that you know stuff. It's good. Right? Or you can just always work through it top to bottom, totally safe. Right? What's the probability notation shorthand? The probability that Z is less than or equal to positive 1.82 is 0.9656. Oh, and I need just a little bit more room, so I'm gonna just bump this up a smidge here. Because what we're really trying to find, the percentage of bottles that pass the quality control inspection. So we're really looking for this area here, right? Lots of ways you could find it, right? Because I have this area, 0.9656, and I have this area that I want to subtract from there, that's a nice way to do it, right? So, therefore, the percentage of bottles that pass QC inspection is 0.9656 minus 0.0344. So I get 0.9312. Whoops. Don't know how I Snuck in another decimal in there. I think I did the percentage as well as the decimal in one in one move. That was silly. Or 93.12%. In shorthand, you could write this as the probability that Z is between negative 1.82 and 1.82 is 0.9656 minus 0.0344, which is 0.9312. Still have to show your work. Doesn't matter which method you use, you still have to show me where you got these numbers from. Okay, that's not just because I'm mean, but it's also, it is that, but, and picky, but it's also so that I can give you part marks in case you wrote something down weird, right? If you show me that this is what you meant to do and then you just have a little calculator error, I'm not bothered by that, that's fine, right? That happens. Okay. So as long as you show me what you meant to do, right, that's what I'm looking for. Okay. So 93.12%, there it is. Whew, this is a lot of work for a multiple choice. Yeah.
Tess, do you want it to be in decimals or percentage?
I'm not going to be too picky. I might ask for the percentage, but I won't take marks off if you give it just as the decimal. It's okay. Yeah. Try to do what I ask you to do, but I understand a test is stressful and I get it. And probabilities are percentages, sort of. Any questions about this one? Before we do an example, working backwards, right? Working the other way. What does that look like? Finally, a new distribution. So here, I call it working backwards often. But I think a lot of the assignment questions call them finding the cutoff points. Okay. So really, solve for X given a probability or percentage. Huh? What's the new distribution that I'm so excited about? Body temperatures. It's not that exciting, I guess, but as you can imagine, people vary, right? We are all centered on some kind of average temperature, but of course, some people kind of run colder and some people run hotter, right? But in general, we're centered on the same value. Now, these are in Fahrenheit, so who knows? Body temperatures of healthy humans are distributed nearly normally with a mean of 98.2 degrees Fahrenheit and a standard deviation of 0.73 degrees Fahrenheit. As soon as you see this sentence structure, right, distributed nearly normally with a mean of this and a standard deviation of that, right, first thing I want you to do is just draw the normal distribution. Okay? And so I know it feels like I don't need that, I can just solve these. You can, but it'll make it a lot easier later on. You just try to draw them. So without even reading the rest of the question, I'll get to work. We're told the shape is normal. Good. It's the only one we know so far. With a mean of 98.2. Wait, did she say so far? I know, right? It's more coming. But by that point, you'll know what's going on. The mean 98.2, and we're told that the standard deviation sigma is 0.73. Good. Now we can read the rest of the question, right? And usually what I have is I give you a kind of a scenario, a distribution like this, and then part A might be, well, if you have a temperature of 104 degrees Fahrenheit, right? That's really high, I think. It's like probably a severe fever / dead, maybe? Definitely hospital. Yeah, really not feeling well. So it'd be way up here. And then what's the probability of having a temperature less than that, right? We can solve that, but that's the same thing we did earlier. Part B, what's the cutoff for the lowest 3% of human body temperatures? Something like that, right? And then part C, what percentage of people have temperatures between these two values? Basically, that's all we can ask. Okay. The cutoff means solving for x. And so for the lowest 3%, now this lowest 3% is what you want to map to an area on your curve. Right? There are some instances where you want to be really careful, right? Because if you think about race times, for example, right? If this was race times instead of temperatures, this is just a heads up because I know it's an assignment question. I'm pretty sure. The fastest 5% would be down here, right? Because they have the lowest race times. And then the slowest people would be up here because they have the highest race times, right? They take the longest. So sometimes you gotta kind of pump the brakes and think about, okay, what does it mean? But most of the time, the lowest 3% maps to the lowest 3%. So here, and we draw this curve only to visualize, right? And so it doesn't really matter. You don't have to spend any time really thinking about where this line is going to go. It's just to help you figure out that, okay, I want to solve for this x. And I'm going to force this area to be 0.03. 3%, it's 0.03. Okay. So we're given some area under the curve and we want to find the cutoff, right? Or some value of x that makes that happen. So we kind of remember our little pendulum. Now I have this probability, this 0.03, and I want to map it back to a z. Right? How are we going to do that? Okay. Feels like there's no rhyme or reason here. But let's think about this for a second. Do you expect to be on the, and I need my little graphic here, the positive side of z is above the mean, right? Versus the negative side of z, I expect it to be negative, right? My z that I'm looking for. Right? So that'll tell me, okay, go to the negative z table. So here I am. And I know it feels like there's no rhyme or reason here, but as you kind of start reading things, right, you have to read them from right to left and top to bottom. Kind of weird. And then they'll be increasing, right? But what you want to do is you want to find the table entry that's closest to 0.03. Okay? Now, there are a couple of things I want to caution, such as, is that 0.03? No. Tempting, right? But you don't want to fall for it. No. 0.03 is somewhere around here. I'm choosing. Looks like these are my two options that are closest to 0.03. You can kind of confirm here, it keeps increasing. If I move up a line, I have to move over to the far, right? That's even further from 0.03, right? So it'll be, I'm choosing between these two values. This is where, if you don't feel in this case, it should be pretty obvious which one is closer, right? They're all going to be some tenth, hundredth, thousandths, 10,000ths off. So I think of this in my brain, this is 1 off. It's not true, but, and this one is 6 off of 0.03, right? That's further. Right? You can use your calculator, whatever you want to do to pick the one that's closest, right? And I'll copy. So now, and paste. Using the Z table, we find the table entry using the terminology that's outlined on the table, right? The table entry closest to 0.03 is 0.0301. Now, the reason that's important for you to tell me is just in case you pick the wrong one, right? Then you're declaring, hey, this is the value that I think is the closest to 0.03. Whether that's right or wrong, right, that's different. Because now if you move forward with what you said, I'm happy, right? So it's all about the procedure. I don't care about the numbers so much, okay? It's always nice when you give me the right numbers. It's easier to mark, right? But I want you to tell me everything, right? Because if you told me for some reason, oops, I don't know why I did that here. For some reason, you didn't do this and you said 0.0239 is the value closest to 0.03. That's wrong, I'll take half a mark off, right? But if you keep moving with 0.0239, just like you said, then I'm happy. Okay? How do we keep moving with this thing? Well, we've decided 0.0301 is the value closest, which maps to, wow, extra boring. Negative 1.8. You're going to think all the Z's start with negative 1.8. They don't. 8. So now this 0.0301 corresponds to a Z of negative 1.88. So we're going to write that down. I guess I shouldn't put a period there. Which corresponds to Z equal to negative 1.88. There. Well, of course, if you had software, Excel, or any sort of online calculator, right, then you could find the Z that maps exactly to 0.03, right, and get a more exact answer. But this is what I'm expecting to see on the test, right, using the Z table. Or again, if you can figure out your calculator, because most calculators do it for Z. I know, motivating, but you'll have the table. So now if Z is negative 1.88, right, what that's saying is that our observation must be 1.88 standard deviations below the mean, right, because it's negative. Huh? So you can use the original equation, which I actually prefer. I personally prefer to have as few formulas as possible that I rework to my needs, right? But I know some people like to have all the formulas reworked so you don't have to think about it, right? And so you could say X is mu plus Z times sigma, which is on your formula sheet, because either way, we're going to solve for X. I'll do both. Maybe I'll do this one in a different color so it doesn't look like I did it twice. There. So if Z is negative 1.88, I'm solving for X minus 98.2 divided by 0.73. To keep it on the same page, what do I have to do? Negative 1.88 times 0.73, then add 98.2. Negative 1.88 times 0.73, do it carefully, plus 98.2, I get 96.8276. I don't want to see any rounding, right? It's not necessary. Or 98.2 plus negative 1.88 times 0.73. Notice that it'll be the same number, but I'll do the negative 1.88 times 0.73, right? Bed mass to multiply before you can add. And plus 98.2. Of course, should be the same. 96.8276. Whichever way you prefer to do it, doesn't matter to me. Okay. Therefore, the lowest 3% of temperatures or body temperatures are up to 96.8276 degrees Fahrenheit. I'm not looking for that final sentence. At this point, I'll just be looking for this number. Did you get it? And if I don't see it, then I backtrack. I know, lazy. But there's a lot of you. It takes me a long time to mark these. So therefore, the lowest 3% of temperatures is less than, I want to keep it on this slide, is less than 96, or are less than 96.8276 degrees Fahrenheit. I'm not looking for that number, but, or that sentence, the number I am looking for. Oh. Just trying to think if there's shorthand for this that I want you to use. Right, technically you could use the same shorthand. I suppose the probability that Z is less than or equal to negative 1.88 is 0.0301. But it's not as telling as that sentence, right? Where you tell me, okay, I go into the Z table, I find the value that's closest, right? and then I map it back to the Z, just working backwards. But you could use that shorthand if you wanted to. Any questions? No. Try again. Same distribution, looks like. And I don't know, some weird, typos, not really, but copy paste. What's the cutoff for the highest 10% of body temperatures? Again, as soon as you see that something is distributed nearly normally, with a mean of 98.2 and a standard deviation of 0.73, right away, you're just going to sketch the curve. Right? Well, that was a pretty good one, I think. 98.2 and the standard deviation of 0.73. We can move a little bit quicker this time, right? The highest 10%. Well, I know that has to be over here somewhere. I want to solve for an x, right? And I'm going to force this to be 10% or 0.1. Right? You can just divide by 100 if you're unsure. You've got some options here, right? The way that we are going to do it is take a step back and say, well, the table only gives me the areas to the left, right? So what I first need to do is find the area to the left, which is of course 1 minus 0.1. So it must be 0.9. That means that I'm looking for an area of 0.9. Kind of a cheeky way that I could do it. And this is not something I'm expecting, but I do want to show you, right? By symmetry, if I force this to be 0.1, right? I could map this back to a negative version of the Z that I want, right? Doesn't save you a ton of time or anything, right? But it's really just about becoming comfortable with the normal distribution, right? And so here, right, because then by symmetry, this x would be at the positive value of that Z. Like I said, I'm going to use the 0.9, but if you try it, right, with using the lower one and then flipping it, right, then you'll find the same answer. So, but like I said, I'm going to use this area. Straightforward, no tricks. So, I'm going to write it out using the Z table. We find the area to, or sorry, the table entry is what we call it on the table. The table entry closest to 0.90 is what? Now, 0.9 is bigger than 0.5, so I know I have to be on the positive Z, right? Positive Z, here we go. And I'm cruising around and I'm looking for 0.9000, right? Or whatever is closest to it. I saw 0.89 caught my eye, 0.89, blah, 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 increasing. And it looks like I'm choosing between these two numbers. Oh, I looked away and now I lost it. There. You're allowed to use your calculator. You don't have to do it in your head. But this one, I would say, is 3 away. And this one is 15 away? I know. That's just my brain. You can think about how your brain works. Use the calculator. All right. How far is it from 0.9? So this value, 0.8997, is the value that's closest. So I'll jot that down. Is 0.8997, which corresponds to some Z. Which corresponds to Z equal to and this is where you want to use some sort of straight edge, right? I usually, when I'm working with the table, I usually take my formula sheet and use it as a straight edge so you're not jumping around so much, right? Up and down is easy enough, but definitely across the table, you don't want to be jumping around. 1.28. So then you would expect this to be negative 1.28. You can try it, right? Check it out if you want to, right? But you'd want to use the positive version because you're on the upper side of the mean. So solving for x, and I'll do it both ways, right? With the original formula, but also, or if you prefer, x is it mu plus, I should make sure I'm doing it the same order, yeah. If z is 1.28, I want to solve for x. The mean is 98.2, and the standard deviation is 0.73. Rearranging these, 1.28 times 0.73 plus 98.2, I get 99.1344 degrees Fahrenheit. Or 98.2 plus 1.28 times 0.73. Making sure that you multiply those two together before you add them to 98.2, but you will find that x is still 99.1344. Or I guess we had options. $99.1, I guess. Yes. So you can find probabilities, or you can be given a probability and have to find the cutoff. Right? Moving back and forth. Nice. Okay, good. Any questions about that one? The 68, 95, 99.7 rule just rolls off your tongue, right? It's also called the empirical rule, but I like to use the more descriptive name, right? So we call it the 68, 95, 99.7 rule, and you'll see why in just a moment. But if you're Googling things, it's also called the empirical rule. But most of the internet will call it the 68, 95, 99.7 rule. for nearly normally distributed data, so that's going to be an important aspect. Yeah. So as long as you have a normal distribution, we already established that within 3 standard deviations, we kind of run out a curve. It keeps going to infinity in either direction, but at that point, we kind of lose interest and say the probability is very, very small, right? And so that's what the 68, 95, 99.7 rule says as well. So what does it mean? Well, about 68% of the curve, so the area under the curve, will fall within 1 standard deviation of the mean. Right? So from the mean, if you move down 1 standard deviation and up 1 standard deviation, the area between those 2 values is roughly 0.68. Okay. Moving on to the 95, any guesses? How about 2 standard deviations? All right, that's exactly it. Okay, so if you move down 2 standard deviations and up 2 standard deviations from the mean, right, then you've captured the central 95% of the curve, right? Which is how we landed on, okay, if you find a Z that's bigger than 2, right, in either direction, then we consider it to be unusual. Why? Because it's in these extreme 5%, right? In fact, 2.5% on the lower end and 2.5% on the upper end split evenly, right? Which it would be by symmetry, right? And so that we would say that's unusual, right? Not impossible, but unusual. Right? So that's where that came from. And then finally, if you move out 3 standard deviations in either direction, you've covered the central 99.7% of the curve. That's a good chunk of 100%, right? Which means how much is split up between the tails? 0.3% in half. So now you have 0.15% in either tail. Very, very, very small, right? And that would be the probability of going beyond 3. Right? It exists, right? But it's very, very small. Now, if we didn't use the tables, right? So these tables that I push on you like it's my product, but I also said I don't like them, must be confusing, I know that. But these tables that we use could be replaced by the 68, 95, 99.7 rule, right? What would the Z table look like? I'll add a page here. All right. So our Z would look like, well, would look like this. And then the probability that Z is less than or equal to, we do this, don't we? Well, that's not very helpful. I'm just catching myself. We do that. That's cheeky. Is less than or equal to Z. I'll just call it the probability. The area to the left of Z. And then I'll move this over here. I'm going to make a very tiny table. All right, why? Because if I've moved down 3 standard deviations from the mean, what does that mean? It means my Z is -3, right? Just by definition of the Z score, right? And so I'm going to start here at -3. Then my next stop is -2, right? Whereas on our table, we start at -3.49, and then we move up by increments of hundredths, right? Until we hit -2, and then we keep going And so it's just been broken down into tiny, tiny intervals, right? And so that's all the Z table is doing, right? But we could do this if we wanted to. -2, -1. Okay, maybe I needed a little bit more room. 0. Right. 1, 2. Just a little bit more room. And 3. How can we do that? If my Z is -3, right? That puts me down here. If I also know that the area between -3 and 3 must be roughly 0.997, right? This area, let's start down here. Okay, so that arrow stops there, which means that this area would be 1 minus 0.997, but that's the total area left over, which we have to cut in half, split evenly amongst the tails, right? Divided by 2. Very, very small. 1 minus 0.997 divided by 2. Of course, 0.0015. It gives me scientific notation, so I have to move my decimal 1, 2, 3. Good. So at a Z of -3, the area to the left, 0.0015. We've got the big table, we can confirm this. All right, if I give it a Z of -3. Now, those are approximations, so I am willing to be a little bit flexible, but not too much. So using the table at a Z of -3, copy this and bring it in. So here versus the table, the difference is that the 68, 95, 99.7 rule is just an approximation, right, about these things. Good enough, though. Is 0.0015 that different from 0.0013? Not really. I'm not terribly concerned about that, right? Versus the table, which yields more precise values. Not as precise as software would, because we still have to round our Z, but kind of halfway. Yes, I do make you do a question with the 68, 95, 99.7 rule, but I say use the 68, 95, 99.7 rule to solve this problem.
Is this something that's important specifically to memorize those numbers, or just more important to understand the idea?
More the concept. As you say, if you say it like 5 times, it'll kind of stick, right? The most important one I would say is the 95, right? 2 standard deviations, right? 68, fine. 95, okay, that's good. And then 99.7 is kind of our upper limit. So now if we have to fill in, well, we don't have to, but I've decided to. This is at a Z of -3. What about a Z of -2? Well, if I've split my 5% evenly amongst the tails, right? Because the total area is still 1, and between -2 and +2, I have the central 95, right? Remember, it's always the central, right? The central 95%. So then this area, oops, is going to be 1 minus 0.95 divided by 2, which is 0.025. We keep moving. To a z of -1. Central 0.68. I lobbed that off. And I split it in half by symmetry. I know it's 16%, but let me just confirm. 1 minus 0.68 divided by 2, phew, is 0.16. What about at the mean? We already established last day, right, that this area must be 0.5. It splits this distribution in half. So, oh, it's kind of a gimme. Right? Because the mean is how many standard deviations away from the mean? 0. So this is at z equals 0. Doing the same thing. Oh, +1 now. I'm gonna already run out of space here. You've got a couple of options, right? Moving into the positive side here, you know by symmetry that the area to the right has to be the same as for -1, right? 0.16. Or you could say, well, it should be 0.16 plus 0.68, right? Add up those areas, right? Whichever way you want to do it works for me. This is going to be 0.16 plus 0.68, which is 0.84. If z is 2, we can do the same thing, of course. By symmetry, it should be the 0.025 plus this full 95%, right, or 0.95. .975. And all of these you can confirm with your table. So close. Okay, here we go. Oops, wrong way. This one has to be the 0.0015 plus 0.997. Better do that one. I want to mix up my decimals. 0.9985. It's a tiny table. We've got a bigger table, kind of more precision, but they do the same thing, right? So we could use the 68, 95, 99.7 rule in the same way that we use the tables or the table so far. And you can use the 68, 95, 99.7 rule to find different areas, right? The same way that we use the table to do it. Well, nice. you can map it back to values, right? Kind of cutoff values. SAT scores, back to that, are distributed nearly normally with a mean of 1,500 and a standard deviation of 300. So if you move down one standard deviation and up one standard deviation from 1,500, you would find that 68%, roughly 68% of students score between 1,200 and 1,800. Right? So it's just a quick way of finding cutoffs most of the time, but also probabilities. 95, roughly 95%. I'll highlight the approximation, right? That's important, roughly. 95% score between 900 and 2,100, right? So from 1,500, you can move down 300, down 300, down 300, right? And have these points. And then it's same for the, don't know why there's a $sign here. Cha-ching. 99.7% score between 600 and 2,400. Right? How much time do I have? Okay, you could get jiggy with it from this. I know, probably we don't say that anymore. But what percentage of students score between 900 and 1,800 on the SATs? Just so then it would say, using the 68, 95, 99.7 rule, what percentage of students score between 900 and 1,800 on the SATs? So what I'm looking for, first map out the area that you want, is this area. Or I guess I should do it like this. All right. Just puzzle pieces, right? What could you do? I'll remove this scribble because it's making a mess. But what if I did something like this instead? Right? I want to find this area. Well, you've got your 68%, but that's between 1,200 and 1,800. So you want to add on this little purple bit. How can you find what that is? Lots of different ways, right? This area here, well, I should use purple to match. Cute. This area, off the top of my head, what am I gonna do? It must be the difference between 95 and 68 split evenly, right? And so here, one way that we could find this area here is 95 minus 68 divided by 2, right? Always remember that symmetry, right? That's the part that trips people up. 95 minus 68 is 27, divided by 2 is 13.5. But that's the area that I want. So I've got 13.5% plus 68%, and that adds up to the area that I want. So then 13.5% plus 68% is 81.5% would be the answer. All right. You could solve that with z-scores in the table, but this is, I think, a little bit quicker. Right? Just rough approximations. Nice. It's a way of talking about z-scores. Which of the following is false? Huh? I'm gonna have to sit down. I almost made it. Almost. So close. Too hot. Oy. I want to talk about A, because A leverages a lot of information. Okay, so the majority of z-scores, so which of the following is false? That's hard. The majority of z-scores in a right-skewed distribution are negative. Whoa. We have to remember what it means to be right-skewed, right? Skewed in the direction of the tail. Okay. And of course, this is great review for your test next week, where you'll need to know this stuff anyways, right? So it's skewed to the right. What do we also know about the mean, right? The mean for a skewed distribution is pulled in the direction of the tail. Right? And so here, it wouldn't be at the median, right? That's why we use the median if you have a skewed distribution, but the mean is pulled towards the tail. Right? And maybe just for emphasis, I'll move it even further down so that we can really see it. Right? The mean is pulled in the direction of the tail. Right? Okay. Now what? Z-scores, we can always calculate Z-scores, right? It's just whether they follow a normal distribution depends on the original distribution, it has to be normal, okay? But Z, remember, is X minus mu over sigma. And if my value of X is below the mean, right? So to the left of the mean, it would be negative, right? And if it's above the mean, it's going to be positive, just like we're used to, right? But now, here I see all my negative Z's. And these guys would be my positive Z's. So the majority of Z-scores in a right-skewed distribution are negative. That's true. Wow, that was a lot of work for a true statement. Boo. Would have been nice if it was false right away. All right. We'll talk about all of them though. So that one looks easy enough, but it uses a lot of information that we've already learned, right? In skewed distributions, the Z-score of the mean might be different than 0. No, we always calculate Z the same way. 0, the mean is how far from the mean? It's 0 standard deviations from the mean, right? So this one is false, but I still want to talk about the rest of them, right? Just because they're good review for your test. I'll clarify Z for the mean is always 0 by definition. Right? Z by definition is the number of standard deviations away from the mean. Right? For a normal distribution, the interquartile range, been a while, is less than 2 times the standard deviation. Oh boy, here we go. So we've got this normal distribution. Mix up my colors here. Got your mean. Oh. Let's start with the 2 standard deviations, just because we just talked about it. All right. And so if I move mu minus 2 times sigma and I move up mu plus 2 sigma, then in here I've got 95%. Right? So I know that 2 standard deviations covers the central 95%. Right? Why am I bringing that up? Because the interquartile range is the central 50%. Right? We know that. Around the median, I know you thought you had me around the median. Well, for a normal distribution, the median is the mean, is the mode. Right? And so here, this is the median, right? In a normal distribution, the mean is the median, and so still counts. And if I go from Q1 to Q3, that distance is the interquartile range. And I know it's shorter because here, and I should have done it, is 50% by definition. I'll remove this 95 and put it up above. It's a little cleaner. Whoops. 95%. Right. So the interquartile range, the distance between Q3 and Q1 or Q1 and Q3, right, is less than 2 standard deviations, right, in either direction. Leveraging those areas. Huh? So that's true. Z-scores are helpful for determining how unusual a data point is compared to the rest of the data in the distribution. That's true. That's why we use Z-scores, right? To assign probabilities, to seeing some observation, but also anything beyond 2, right? We have this internal flag that says, oh, maybe this is an unusual observation, right? And so I don't think there's anything to write about that one. There's nothing to kind of background, but that's why we use Z-scores. Right? Okay. Whoa. I do want to do the next section, but it'll be brief. Any questions though before we leave the normal distribution? Now you'll be able to do that assignment that I posted. No, rude. Should have warned you. The geometric distribution is this next section, and I am sneaking it in because we need to introduce a couple of concepts before we go into Thursday. Okay. And so the geometric distribution is not tested. But I will post a bonus assignment which includes the geometric. But we use it to introduce some core concepts leading into our next distribution, which is the binomial distribution. So it's kind of a stepping stone distribution. Geometric distribution. And the reason I have to talk about this is because it uses, looks like someone's familiar with the Milgram experiment. We refer to this experiment in the next section as well, so we should probably know what's going on. And it's an interesting experiment. They could do whatever they wanted, even in the 60s, I guess. So Stanley Milgram, a Yale University psychologist, conducted a series of experiments on obedience to authority starting in 1963. Like I said, it's kind of hard to get ethics approval now, but we learned a lot, I guess. Experimenter E. So here we have the experimenter orders the teacher, me, I guess, the subject of the experiment, right? So I'm the little mouse in this situation. So I'm instructed to give severe electric shocks to a learner sitting here each time the learner answers a question incorrectly. Uh-oh, That's mean, right? The learner is actually an actor and the electric shocks are not real, but a pre-recorded sound is played each time the teacher administers an electric shock, right? So the teacher thinks it's real and they think they're shocking their student every time they answer something incorrectly. Right? And so again, it's an experiment on obedience to authority. I've been told to do this. I have to do it, guys. And maybe. So these experiments measured the willingness to study participants to obey an authority figure who instructed them to perform acts that conflicted with their personal conscience. Of course, I don't want to shock you. It would probably go something like this. I don't want to shock you, but I have to. Right? That's how it is. Milgram found that about 65% of people would obey authority and give the shocks. That's pretty high, right? Kind of concerning. Right? So now, the probability that someone administers the shock is 0.65, right? That's what we're told. So the probability of a shock, we're told, is 0.65. Okay. Over the years, additional research suggests this number is approximately consistent across communities and time, right, which is even more interesting, right? Things kind of just, this number tends to be the same, right? So I find that interesting. Bernoulli, famous statistician / mathematician. And so what we call a Bernoulli random variable is broken down into trials and successes and failures. And so each person in Milgram's experiment can be thought of as a trial. And so each teacher, I think, specify that here. Each teacher, a person is labeled as a success, and here's the confusing part. If she refuses to administer a severe shock, not that confusing because it's a positive. Now, often a success is the thing that we're interested in, right? So a success is getting a disease that you're studying, right? So a success is often kind of morbid. Here they've flipped it to be cute, I think, but so a success in this case is if she refuses to administer the shock. That'll be important later. And a failure if she administers the shock. Which means that what we said earlier, this is the probability of a failure, 0.65, which means the probability of success is 1 minus 0.65, just by the complement rule. So since only 35% of people refuse to administer a shock, the probability of success is p 0.35. So p, a lowercase p, is used to denote a success or the probability of success. So we're told that p in this case is 0.35. Now, we've already seen this kind of success failure situation, right? And so when an individual trial, right, so each teacher that steps into the experiment has only 2 possible outcomes, right? They either shock them or they don't, right? So a failure or a success in order. It's called a Bernoulli random variable, right? Only 2 possible outcomes is what it summarizes to. Only 2 possible outcomes. Right, success, failure. Often we can create a Bernoulli random variable, right? If it helps us solve a problem, right? we've seen that before, right? I can't think of the exact example, right? But if you roll a die and you're interested in rolling a 5, for example, then you could say, okay, the probability of rolling a 5 is 1 in 6, which means that the probability of rolling not a 5, right, anything but, is the complement, 5 in 6. So I like to use a lowercase q. Q is going to be shorthand for the probability of a failure. Is used to denote the probability of failure. Which means that Q must be 1 minus P, right? By the complement rule. It's only 2 options, right? There's no overlap. And if you look on your formula sheet, you have to squint a little bit, I guess. But look at us, just ripping through this formula sheet. It's at the very, very bottom, actually. Note, lowercase q is the probability of a failure, so q is 1 minus p. Have it on there, but I do expect you to know it because I use it in our formulas. Okay, so the geometric distribution is a special case that I'm not terribly interested in, but we use it to build up to the binomial. So Dr. Smith wants to repeat Milgram's experiments, but she only wants to sample people until she finds someone who will not inflict a severe shock, right? And so until she hits a success. What's the probability that she stops at the first person? Well, the probability that the first person refuses, right? You know how to solve this. You don't need it to be called the geometric distribution. We could use our slots, right? And force the scenario that we want, right? And so it's a refusal, which had a probability of 0.35. And that is the probability of stopping at the first person, right? Because they refused. What if we want to find the probability that she stops after the third person? You know how to solve that, right? You could say, okay, well, 1, 2, 3, she's only going to stop once she has a refusal, right? Which means that the first 2 must be shocks, right? Shock, shock. Shock and refusal, right, is the scenario. And so then we have 0.65 times 0.65 times 0.35. They've done it in a different kind of, we use the same slots, but they've done the probabilities below, but I've been doing them above, so I'm keeping it the same. So you have the probability of a failure, right? Shocking, or shocking the learner, to the power of 2 times the probability of a refusal, right? 0.35, because you always have to end on the refusal. You can do the same thing for the 10th person, but I don't want to draw out all those slots, 10 slots. It would be shock, 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 shock 9 times, followed by a refusal, right? 0.65, the probability of a shock for the first 9 people, followed by a refusal, right? And we can calculate those probabilities. They get smaller and smaller, right? So this is what the geometric distribution does for us. It's a special case, but the geometric distribution describes the waiting time until a success, right? For independent and identically distributed Bernoulli random variables. You don't have to worry about that, but it is technically correct to say it, so we should. The independent part comes from the outcomes, the probabilities are independent of each other, right? Each teacher who steps in, we assume they didn't talk to each other, that kind of thing, right? So the probability of the teacher shocking the student stays the same, right? So they're independent. And then the identically distributed is that the probability stays the same, right? So we've just summarized that as independent. If P represents the probability of success and 1 minus P, or shorthand Q for me, right? PQ is pretty common. 1 minus P or Q, which is 1 minus P, represents the probability of failure. And N represents the number of independent trials, right? Then the probability that the first success that you see is on the nth trial, okay, must be, you have N minus 1 failures, right? Probability of failure to the power of N minus 1. And then your last one has to be a success. Okay? And so this is the geometric distribution. We're still finding probabilities, but not really in the same way. And I know. We already talked about this one, so I'll highlight it. I know I am gonna rip through it. How much time do I actually have? No time. 1 minute, I can do it. Because we're not gonna use it, so I'm not that concerned about it. We can still find an expected value and a standard deviation for a geometric distribution. The mean for a geometric distribution is going to be 1 over P, kind of fun and interesting, but again, not on the test. With a standard deviation of 1 minus P over P squared, square rooted, kind of fun. So we can calculate these. And there, now we're ready to pick up with the binomial, which is an extension of the geometric on Thursday. If you have any questions, let me know. Otherwise, see you then.